Hi everyone. Welcome to the second talk on neural harmony by Dr. Grover. And I'm very excited. This is the 21st session from Silicon Valley Quantum Computing Group. It started as a fun project, and I am super excited. It's going, and I have top leaders and top scientists coming and speaking here. So it's super impressive to see them. About me, I am the Director of Innovation and AI for a healthcare company called Kaiser Permanente. I am the author of two books, Medical Image Processing with Deep Learning, and then Intelligent Governance, especially in the AI and the quantum space. I might have a second version for the Intelligent Governance coming up next year, so I'm in the process of writing it. Uh, I am currently at Harvard Medical School, and I am doing a master's on bioethics right now. With that, I'll talk about Dr. Grover. Dr. Grover holds a PhD and MSc from the University of Delhi in the South Campus. He's been heading and leading the Center of Agriculture Bioinformatics. He's in from at Amity University, and his career includes postgraduate or postdoctoral postdocs at Colorado State University and Penn State University. As you know from his prior talk, he is a researcher. He is one of the eminent scientists, and I'm glad that he's come back here to finish part two of his work. Um, so the idea is we will first have a talk from Dr. Grover, and then we'll spend like few minutes and have discussion. We'll open it up for questions, and we'll take it from there.
So we will be talking about quantum computing today in agriculture because I work in an organization which is Indian Council of Agricultural Research, which is the main government body controlling or organizing the research in agricultural research in India. And basically, I am a molecular biologist, and my journey into quantum computing started from biology. So when I was doing my postdoc at Penn State University in around 2004, I became interested in consciousness. So on a visit to my friend's house, I saw a book by Roger Penrose, Shadows of the Mind. So when I came back, I ordered that book and I went through it. And that was an interesting hypothesis on, there was an interesting hypothesis on consciousness in that book. And it was related to quantum computation. So I became familiar with quantum computation reading that book. And then I searched quantum computing, and gradually I continued my research in consciousness, quantum computing. So at that time, around 2004, there was not much research in the practical quantum computation. So as the time passed, there was increasing amount of research in quantum computation. And in India, last year, government announced National Quantum Mission, which was around 6,000 crore rupees. Uh, I don't know in billion dollars how much it is, but 6,000 crore rupees they announced for quantum computing research. And we have submitted a quantum computing. We want a quantum computing facility for agriculture in Indian Council of Agricultural Research. So we have submitted a 200 crore rupees project, and I'm glad to share with you that we have cleared the first stage. And we hope that we will have quantum computers in ICR, and we will be embarking into our journey of quantum bioinformatics in agriculture. So that was my introduction, my journey in quantum computation. Now, on to today's talk. Unveiling the quantum frontier in agriculture, a journey into the promise and power of quantum computing. Now, in the ever evolving landscape of technology, one phenomena has captured the imagination of scientists, researchers, and innovators alike: quantum computing. Touted as the next revolution in computation, quantum computing has the potential to solve complex problems that are currently beyond the reach of classical computers. So we have classical digital computers right now with us, and they are solving a lot of problems, but there is big data, there is huge data which needs to be analyzed with considerable speed. So digital computers are not so particularly efficient at handling that big data or the huge amounts of data. So quantum computers have come into foreground, and they are revolutionizing our vision of computation. And they have the potential to solve complex problems that are currently beyond the reach of classical digital computers. This is the picture of quantum computation. You see, it is a big machine like the digital computers were when they were just initiated. And it is a big machine, and gradually it will become smaller as digital computers became. So quantum computers, they are still in their infancy, and a lot of countries and private organizations all over the world have pumped money, lot of money into quantum computing research, and they are gaining ground. Now, as we stand on the precipice of a new era in computing, it is essential to understand what quantum computing is, how it works, and the groundbreaking implications it holds for various fields. So we need to understand what is quantum computing, how it works, and what are the implications for various fields. Now, quantum computing derives its power from the principles of quantum mechanics, a branch of physics that deals with the behavior of matter and energy on a subatomic scale. Now, unlike classical computers, which use bits to represent information as zeros and ones, so in classical digital computers, the information is represented as bits, which can be either 0 or 1. And now, in contrast to classical digital computers, quantum computers utilize quantum bits or qubits. Now, qubits can exist in a state that is combination of 0 and 1, which is represented by block sphere. So we won't go into the details of that, thanks to phenomena called superposition. So in digital computers, we have zeros and ones. In quantum computers, we have three states, 0, 1, and 0 and 1 in various degrees of superposition. Now, this unique property enables quantum computers to perform multiple calculations simultaneously, vastly increasing their computational capacity. So it is 2 raised to power n for n bits in digital computer, and 3 raised to power n because 3 states are possible in quantum computers with 3 possible states for each qubit. So this is a cartoon for superposition. So there was a famous Schrodinger's cat experiment, which is used to describe superposition. We won't go into the details of it, but what you can see here is that this is very counterintuitive, especially at the macroscopic levels. But at microscopic levels, this is more common. So this is dead cat, this is dead cat, this is alive cat, and this is 0, this is 1, and this is 0 and 1 superposed together. That is, cat is dead and alive at the same time. Now that may sound nonsense. At macroscopic, it may sound nonsense, but at microscopic levels, at the levels of electrons, neutrons, protons, and other elementary particles, these states are routine. Now, another intriguing aspect of qubits is entanglement. Now, when qubits become entangled, the state of one qubit becomes dependent on the state of another, regardless of the physical distance between them. So as I told you, in digital computation, there are bits, and in quantum computation, there are qubits. Qubits show another property besides superposition, which is entanglement. So what is entanglement? The state of one qubit becomes dependent on the state of another, regardless of the physical distance between them. So much so that it is hypothesized that if two particles are at the end of the universe, even then the state of one entangled qubit will depend on the state of other entangled qubit on the other side of the universe. So distance is not a matter of concern. Now, this property allows quantum computers to perform certain calculations much faster than classical computers. So this is a cartoon of entangled particles. This is observed here, and this is affected over there. So there is entanglement between them. So if these are two entangled particles, and if one particle is affected here, the other particle will be affected there, and there is no physical connection between them. So there have been a lot of speculations that what is the nature of communication, so-called within inverted commas, between them, but there is no consensus as yet. Now, harnessing the power quantum computing technologies. At the heart of quantum computing lies the quantum gate, the equivalent of the classical logical gate. So in digital, you have logic gates, and in quantum computing, you have analogous quantum gates. Now, quantum gates manipulate qubits by altering their state based on the principles of superposition and entanglement, which we have discussed. Now, assembled in quantum circuits, these gates execute complex operations with incredible speed and efficiency. So this is a picture of qubit and its logic gates. So this is we won't go into the detail of the picture, but this represents the superposition between 0 and 1 in various degrees. This is called a block sphere, and this is a representation of a Hadamard gate. Now, several technologies are being explored for building quantum computers, each with its own set of advantages and challenges. Superconducting qubits, trapped ions, and topological qubits are some of the leading contenders of the technologies being explored for building quantum computers. Now, companies like IBM, Google, and Intel, as well as startups such as Rigetti and IonQ, are making significant strides in developing practical quantum computing systems. So this is superconducting qubit technology. There are three types of superconducting qubits: charged qubit, phase qubit, flux qubit. We don't have time to go into the details of this, but it is sufficient to remember here that there is one technology. There is one of the technologies is superconducting qubits. Another is trapped ion quantum computers. Another is topological qubits. And now we will talk about quantum supremacy, that how the quantum computation is better than the digital computation. Now, a significant milestone in the realm of quantum computing was achieved when Google claimed to have achieved quantum supremacy. In 2019, they announced that their quantum computer Syamore successfully performed a calculation that would take the world's most powerful supercomputers, that is digital computers, thousands of years to complete. So this event marked a turning point, demonstrating that quantum computers could indeed solve problems beyond the capabilities of classical machines. Now in June 2022, Xanadu has reported on a boson sampling experiment summing to those of Google and USTC. So they have reported an improvement on the experiments I just mentioned, Google Syamore 2019. Their setup used loops of optical fiber and multiplexing to replace the network of beam splitters by a single one, which made it also more easily reconfigurable. And they claim to have obtained a speed of 50 million times bigger than the previous experiments. So there is a huge increment in the speed up, even beyond that observed in 2019 by Google. However, the concept of quantum supremacy is still debated among experts. Now, while the specific calculation Google Syamore performed was designed to showcase its capabilities, it doesn't directly translate to solving practical problems yet. So although quantum supremacy was demonstrated in two experiments and in many more experiments, not only two, but it is directly implementing it into solving practical problems is still a far cry. Many believe that quantum computers will truly shine when they can solve real world challenges in fields like cryptography, optimization, drug discovery, and material science. Now, the potential applications of quantum computing span a wide range of industries. In cryptography, quantum computers could render current encryption methods obsolete by quickly factoring large numbers, breaking many existing cryptographic systems. This has led to the development of quantum-resistant encryption methods to safeguard data in the post-quantum era. So, quantum computing has tremendous application in cryptography. Now, in the realm of, it has applications in the field of optimization also. In the realm of optimization, quantum computers holds the promise of revolutionizing supply chain management, financial modeling, and complex system analysis. These machines can quickly evaluate numerous possibilities and identify optimal solutions, tackling problems that are practically insurmountable for classical computers. So problems which are impossible for classical computers can quickly be solved by quantum computers, at least in theory. Now, pharmaceutical and materials science industries are also poised to benefit from quantum computing. Quantum simulations can accurately model molecular interactions, which are important in drug discovery, leading to the discovery of new drugs and materials with unprecedented efficiency. This could potentially accelerate the development of life-saving medications and innovative materials. Now, what are the challenges on the quantum horizon? Now, despite its incredible potential, quantum computing faces significant challenges. Qubits are incredibly delicate and prone to errors due to their susceptibility to environmental interference. So entanglement and superposition, which we discussed, they can be disturbed by environmental interference. So that is why the quantum computers are isolated from environment to avoid any environmental interference. Researchers are diligently working on error correction techniques to mitigate these issues and create more stable qubits. So qubits by nature, they are inherently unstable. So to make them stable, researchers, to how to make them stable, that question is being addressed in many studies. Now, cooling and isolation techniques are also crucial to maintaining the delicate quantum states required for computation. Now we will talk about quantum computing hardware, unveiling the quantum wonders, decoding the marvels of quantum computing hardware. Now, diverse quantum platforms, the battle for supremacy. Quantum computing hardware is not a monolithic entity, but a universe of technologies vying for supremacy. Among the front runners are superconducting qubits, as we saw, trapped ions, and topological qubits, each with its own merits and quirks. We have talked about superconducting qubits, trapped ions, topological qubits. Now, what are the challenges for quantum hardware? Now, the quantum hardware landscape is not without its tribulations. The biggest hurdle is the decoherence, which causes qubits to lose their delicate quantum states due to interactions with the environment. So this is interaction with the environment is leads to disturbance. So this disturbance is to be avoided for efficient quantum computation, and research is going on. Error correction, we have talked about cryogenics and cooling and scaling up. Now, quantum supremacy has been achieved with relatively small number of qubits. However, to tackle complex real-world problems, quantum computers need to scale significantly. This necessitates not only adding more qubits, but also maintaining their coherence as the system becomes more complex. So quantum supremacy has been demonstrated with relatively few qubits, but to tackle real-world problems, we need more number of qubits, and the problems crop up as we discussed. Now we will talk about quantum software. Now, in the quest for computational supremacy, quantum software emerges as the orchestral conductor of the quantum symphony, guiding the ethereal dance of quantum bits through the intricacies of complex calculations. Now, quantum software serves as the bridge between the esoteric realm of quantum mechanics and the tangible world of computation. Just as classical computers rely on programming languages like Python or Java, quantum computers have their own set of languages tailored to exploit the unique attributes of quantum bits or qubits. So quantum computers, they have their own set of languages. The most widely used quantum programming languages, including Qiskit, developed by IBM, Cirq, created by Google, and QTIP, a powerful tool for simulating open quantum systems. These languages allow researchers and developers to write algorithms that manipulate qubits, harnessing their superposition and entanglement properties to perform calculations that would be infeasible for classical computers. Quantum algorithms cracking the cryptic code. Now, among the most celebrated quantum algorithms is Shor's algorithm, capable of factoring large numbers exponentially faster than any classical algorithm. So Shor's algorithm and Grover's algorithm. So that Dr. Grover of Grover's algorithm is not related to me, by the way. And this has profound implications for cryptography, potentially undermining current encryption methods and sparking a race to develop quantum-resistant alternatives. So two kind of algorithms are most popular. There are many quantum algorithms, but Shor's and Grover's were one of the first. Now, Grover's algorithm, as I mentioned, another quantum marvel, offers a quadratic speed up in searching through an unsorted database, a task that grows exponentially on classical computers. On classical computers, this task is difficult. This could revolutionize optimization problems, enhancing industries ranging from finance to logistics. Now, from theory to reality, quantum software applications. The transformative power of quantum software cascades across various industries, poised to revolutionize sectors where computation is paramount. As I discussed earlier, also in the realm of drug discovery, quantum software can simulate molecular interactions with unprecedented accuracy, expediting the identification of potential safe living life-saving medications. Similarly, material science stands to gain as quantum simulations unveil new materials with tailored properties, revolutionizing industries from electronics to renewable energy. Machine learning also experiences a quantum boost. Now, quantum machine learning is another field altogether. And in quantum machine learning, quantum neural networks such as the quantum Boltzmann machine can efficiently perform tasks like pattern recognition and optimization. This promises significant enhancements in artificial intelligence, leading to smarter decision-making systems. Now, challenges and complexities of the quantum software landscape. So as I told you before, quantum noise and error corrections and errors, they are persistent problems. Now, additionally, translating classical algorithms to quantum counterparts isn't always straightforward. Quantum parallelism, the heart of quantum computing's power, can lead to algorithmic intricacies that demand creative thinking. Now, now we will talk about quantum leap in agriculture, cultivating a greener future with quantum computing. Now, we will talk about quantum leap in agriculture now. Now, in the vast fields of technological and advancement, an emerging force is poised to revolutionize agriculture and industry foundational to human sustenance and progress. Quantum computing, with its capacity to tackle complex problems that have long eluded classical computers, is ready to plow through the challenges faced by agriculture. From optimizing crop yields to tackling climate change related issues, quantum computing promises to be a plow that furrows a path toward a more sustainable and prosperous agricultural future. Now imagine optimizing the irrigation systems of a vast agricultural estate to conserve water while ensuring each crop receives the ideal amount. So we have a saying in agriculture, more crop per drop. So for a given amount of water or for a given drop of water, we need more crop. So for that, we need to optimize irrigation systems. And it is a part of precision agriculture or ultra precision agriculture. So optimizing the irrigation systems of a vast agricultural estate is difficult with classical or digital computers because there are a huge number of possibilities, but quantum computers could simultaneously evaluate numerous scenarios to determine the most efficient strategy. Now, crop optimization. One of the most promising applications of quantum computing in agriculture lies in crop optimization. Quantum algorithms can analyze data about soil composition, weather patterns, and crop genetics to fine-tune planting times, irrigation schedules, and fertilization practices. This can lead to higher yields, reduced resource usage, and minimized environmental impact. Moreover, quantum simulations can model intricate biological processes, allowing for the development of drought-resistant, disease-resistant, and higher nutrient crops. So by rapidly exploring different genetic combinations, quantum computers can fast-track the breeding of improved crop varieties, ensuring food security in the face of changing climates. So, in fact, this is what we have proposed in our proposal to National Quantum Mission that we will study the intricate biological processes, the molecular details of drought-resistant, disease-resistant, and higher nutrient crops, and we will use molecular dynamic simulations and quantum computers are very efficient at molecular dynamic simulations, and we will perform all the other techniques to reach the drought resistant, disease resistant, and higher nutrient crop stage. So for molecular breeding, quantum computing can be a godsend opportunity. Now we will talk about the quantum advantage. Now, quantum computing holds substantial potential for applications in biology and medicine, spanning from simulation of biomolecules to machine learning methods for subtyping cancers on the basis of clinical features. This potential is encapsulated by the concept of a quantum advantage, which is contingent on a reduction in the consumption of a computational resource, such as time, space, or data. So quantum computers, they save on computational resources such as time, space, or data. Now, quantum computing past to present, we have now the notion that a quantum computer may be powerful than a classical computer was first conceived some 40 years ago in the context of simulating physical systems. Theoretical models of quantum computers quickly followed. And then in 1993, 11 years after the Feynman's talk on simulating physics, early formal evidence that a universal quantum computer may be more powerful than its classical counterpart arrived with the proof of a quantum advantage on an artificial problem, that is recursive Fourier sampling. So Feynman was the pioneer of quantum computers. This was shortly followed by the development of the first quantum algorithm for a practical problem, prime factorization, by Peter Shor in 1994, also yielding a super polynomial advantage. Now, Shor's algorithm was the first example of a quantum algorithm that could have significant real-world implications by threatening the RSA crypto system, which is widely used to secure the web. Now, its discovery initiated a flurry of research into quantum algorithms, and now burgeoning subfield of quantum information science that has continued to the present. So I discussed about this 2019 experiment by Google. Now, after Google and after Xanadu in 2022, similar experiments leveraging various quantum hardware technologies have followed. While it has been debated whether these experiments represent true examples of quantum supremacy, they have nonetheless galvanized the QIS field around the practical potential of quantum computers in the near term. So although these experiments which demonstrate quantum advantage like Google's in 2019, Xanadu in 2022, and now numerous others, they are still theoretical, but they have nevertheless demonstrated the importance of quantum computers. Now, quantum hardware has now entered the noisy intermediate scale quantum era, the NISQ era, a stage of maturity characterized by devices with low qubit counts, high error rates, and correspondingly short coherence times. So now currently we are in noisy intermediate scale quantum era, NISQ era, which is characterized by devices with low qubit counts, which is of course, which needs to be replaced with high qubit counts, high error rates, which needs to be replaced by low error rates, and correspondingly short coherence times. So for efficient computations, we need higher coherence times. Now, while it is unclear how long the transition from the NISQ era towards fault-tolerant quantum computation, which is an ideal stage, will take, we need to move to FTQC stage. Whether it will occur by error correction or inherently fault tolerant hardware based on topological properties, estimates range from several years to several decades. So we may take from several years to several decades, go into the FTQC, that is the fault tolerant quantum computation era. Yet with NISQ devices moving from the laboratory to the cloud, now is an opportune time for computationalists in biology and medicine to begin exploring the value that quantum approaches bring to their research toolbox. Now, biology and medicine as computational sciences. Over the past 3 decades, biology and medicine have evolved into highly quantitative fields. Now, Previously, it was qualitative in the early years, but now it has evolved into highly quantitative fields. Areas of inquiry span from foundational questions on the origins of life and the relationships between protein structure and biological function to ones with a direct implication on clinical practice, such as those concerned with the oncogenesis of cancer, the development of novel drugs, and the precise targeting of therapeutics on the basis of genetic mutations and other clinical indicators. Quantum computation, they have a wide range of application in biology, since biology has evolved from a qualitative science to a highly quantitative science. Now, however, despite the substantial progress facilitated by computational methods and the expansion of high performance computing environments, fundamental constraints persist when modeling biological and clinical systems. System complexity is one example. Now, this constraint arises from both the first order biological complexity, as can be seen in the metabolic processes of individual cells. So when we are modeling complex systems such as metabolic systems, now it is not trivial, and there are several constraints. So it can be seen in the metabolic processes of individual cells or the binding of protein receptors to ligands, and the higher order clinical complexity occurring at the intersection of complex biological, behavioral, socioeconomic, cultural, and environmental factors. On the one hand, this system complexity has made and biological and clinical research a verdant playground for the development of many novel, efficient computational algorithms and approaches. On the other hand, practical algorithms typically manage system complexity via reductionist frameworks, which is not very efficient and which may not represent the biological system under study very optimally or very efficiently. A consequence of this is that existing computational models often fail to capture and reconcile important system dynamics. Perhaps the clearest examples exist in the fields of structural biology and biochemistry, where even simple biological molecules such as proteins, ligands, and transcription factors regularly challenge classical heuristic methods developed to model their structure and binding behaviors. So modeling in biology is not very simple, more so in structural biology and biochemistry. Now, quantum computers, if sufficiently robust ones can be built, promise to fundamentally reduce the algorithmic complexity of constructing and analyzing many of these models. This may allow solutions to hard computational problems to be computed with greater algorithmic efficiency, which it could in turn reduce compute times and improve the fidelity of practical models. So quantum computers could reduce compute times and improve the fidelity of practical models. The second constraint is one of scale. Looking to healthcare alone, as much as 153 exabytes of data were generated in 2013. This data is a little old, with a projected annual growth rate of 48%. Extrapolating this growth rate, it is possible that over 2,300 exabytes were generated in 2020. Similar data challenges also exist in biology. For example, the massive growth of high throughput sequencing has led to exabytes of highly complex genomic, epigenomic, transcriptomic, proteomic, and metabolic data types, among others. To manage these large data volumes, centralized data repositories have proliferated, e.g., you can see the ever-growing DBGAP or more recent Genome Data Commons. These massive data resources are crucial to the reuse of high-value data in secondary analysis and reproducibility studies. However, even with the wide use of HPC, that is high performance computing infrastructures, large bioinformatics and computational biology workflows often extend for days, weeks, or longer. In recent years, this challenge has grown with the expansion of other areas demanding significant computational resources. So analysis in biology and computational biology, biochemistry and structural biology, it is a huge data problem, and it may take, even with HPCs, that is high performance computing systems, days, weeks, or longer. And this time has considerably grown with demanding significant, with expansion of other areas demanding significant computational resources. Now, examples include high resolution imaging, e.g. cryo-EM, and massive deep learning inference pipelines with the order of 109 or greater model parameters. While it is not anticipated that scalability constraints will be addressed by quantum computing technologies in the near term, FTQC devices may offer a partial solution to some of these challenges over the long term. Now, given these challenges across biology and medicine and the potential of quantum computing, a common question among domain computationalists interested in applying quantum computing is, when will I be able to leverage quantum computing for one can insert preferred application? The answer to this question is complex and can be factored into a number of considerations. So when will the quantum computing have practical advantage for domain experts? This is a complex question and we will try to answer this. It can be factored into a number of considerations. Now, how can it be ascertained whether a problem will benefit from a quantum advantage? That is the first question. What scale of problem instance is required to meaningfully demonstrate such an advantage? Second question. What hardware and software are required to translate a quantum advantage from theory to practice? Third question. How can a practical quantum advantage be detected and measured once it has been achieved? This is the final question. Now, the landscape of quantum advantages. Now, the landscape of quantum advantages is a set of concepts that together are central to the identification, characterization, and realization of quantum advantages. Now, these concepts which we present below include a classification system scheme for quantum advantages, context-based evidence levels for establishing their existence and practical realization, and known hardware constraints that can influence their practical implementation. Theoretical quantum advantages. How can we define a quantum advantage from the theoretical perspective? Now, while multiple mathematical formulations have been described in the literature, for our purposes, we simply state that a theoretical quantum advantage is defined by four key properties. Problem, a formal computational problem, algorithms, a classical algorithm and a quantum algorithm, each of which solve the computational problem, resources, one or more resources such as time, space, or data that are consumed by both the classical and quantum algorithms, bounds, analytical bounds on the resource consumption, e.g. worst case time complexity bound for both the classical and quantum algorithms. Classifying theoretical advantages. A theoretical advantage, quantum advantage, can be classified on the basis of two factors. The first one relates to the classical hardness of the computational problem, which is defined by the best known classical algorithm or provable upper bound. In particular, a computational problem may be classified as easy or hard according to whether its classical algorithmic complexity is polynomial or super polynomial respectively, typically for a worst case input. The second factor relates to the size of the advantage yielded by the quantum algorithm relative to classical algorithm. Often these advantages result from a reduction in complexity for a computational resource. Here we would like to make clear that the terms easy and hard refer only to classical computability. They are not intended to refer to the attainability of a practical quantum advantage or the difficulty of implementing a quantum approach. Now, what are the context-based evidences for quantum advantages? A quantum advantage may be supported by multiple forms of evidence that can vary by its context. At the highest level, these contexts can be theoretical or empirical. In the theoretical context, abstract evidence is collected to answer whether a quantum algorithm can yield an advantage over the most efficient classical algorithm. By contrast, empirical evidence is collected to answer whether a specific quantum algorithm and device can together yield an observable advantage over a classical approach. So the main point is that what is the advantage of quantum algorithms or quantum hardware over the classical approach, given a well-defined problem and context-dependent metric. Now, importantly, while an experimental advantage may also be practical, evidence from an operational setting is best suited to addressing questions around the practical value of an empirical quantum advantage. In this section, we describe these contexts in detail and their implication for the evidence required to establish a quantum advantage. So in this section, we will deal how to come to the evidence required to establish a quantum advantage. Now, what are the theoretical advantages of quantum computation? Now, these result from an improvement in analytical bounds on resource efficiency by a quantum algorithm relative to a well-motivated classical counterpart. The core resource in question typically involves units of time, space, or information, e.g. samples from an experiment. In practice, these units of comparison may be gates, queries, bits, or error rates. So you may compare gates, queries, bits, or error rates in classical computation and digital computation. Now, theoretical advantages are defined mathematically, may be conjectured, and are often contingent on well-defined assumptions from computational complexity theory. Crucially, they need not be application-oriented. Instead, they may be conceptual, designed with the express intent of demonstrating that an advantage exists for an artificial task or broader class of problems that have theoretical interest. Now, examples of conceptual quantum algorithms yielding theoretical advantages include the Jozsa algorithm, Bunstein-Vaziriani algorithm, Simon's algorithm, and one for solving the correlation problem. Now, despite their theoretical motivation, practical applications may nonetheless follow from conceptual algorithms. One example of this can be seen with Shor's algorithm for prime factorization, which was inspired by Simon's algorithm. So theoretical advances are also very important, even from a practical application point of view. Now we discussed about theoretical quantum advantages. What are experimental quantum advantages? These are a type of empirical quantum advantage observed in an experimental context. Crucially, they require the comparative analysis of computational metrics that precisely measure the advantage in question. Now, to facilitate these comparisons, these metrics are ideally defined over both quantum and classical approaches. While theoretical evidence, that is proofs, conjectures, and numerical models, may support an experimental advantage a priori, it is the computational benchmarking of an implementation that serves as the evidence for establishing an experimental quantum advantage. For instance, the first quantum supremacy experiment represented a real-world demonstration of an experimental quantum advantage. First, a theoretical advantage was proven and numerically estimated. Then initial experimental work soon followed, which yielded the first hint of such an experimental advantage. So this was a sequence of events. First, a theoretical advantage was proven, numerically estimated. Then initial experimental work followed, which yielded the first hint of such an experimental advantage. Now we have talked about the quantum advantage. Now we will focus our attention to climate modeling and prediction, navigating agricultural resilience. Now, climate change poses a significant threat to global agriculture, altering growing seasons, precipitation patterns, and exacerbating extreme weather events. Quantum computing's prowess can aid in creating highly accurate climate models, which are very complex. So quantum computers can be handy in constructing highly accurate climate models, enabling farmers to anticipate shifts in weather and adapt their practices accordingly. Now, quantum algorithms can analyze a myriad of variables such as temperature, humidity, and wind patterns to predict weather conditions with unprecedented accuracy. This information can guide farmers in making informed decisions about planting, harvesting, and resource allocation, mitigating potential losses caused by unpredictable weather. Now, supply chain optimization, farm to fork efficiency. Now, quantum computing's aptitude for optimization extends beyond fields and into the intricate web of agricultural supply chains. By optimizing the logistics of transporting produce from farms to markets, quantum algorithms can reduce food waste, energy consumption, and overall costs. This has profound implications for both economic efficiency and environmental conservation. Additionally, quantum-powered simulations can model supply chain scenarios, accounting for factors such as transportation routes, storage conditions, and demand fluctuation. This aids in strategic decision-making, ensuring that food distribution is efficient, timely, and responsive to market demands. Challenges and cultivating collaboration. Now, while quantum computing holds immense promise for agriculture, challenges persist. Quantum hardware sensitivity to noise and environmental interference, which I have been repeatedly emphasizing throughout my talk, can impact the accuracy of calculations. However, as technology evolves, these challenges are likely to be overcome through error correction techniques and refined algorithms. For quantum computing to truly flow through agricultural challenges, collaboration between experts in quantum physics, computer science, and agricultural science is paramount. Governments, research institutions, and agribusinesses must join forces to harness the potential of quantum computing in agriculture. Now, as the world grapples with the growing population and environmental challenges, the role of technology in securing a sustainable future becomes even more critical. Quantum computing's potential in agriculture is akin to finding a new fertile land, one that offers solutions to problems that have stymied us for generations. Now, unlocking the code of life, quantum computing's roles in bioinformatics revolution. So bioinformatics is the science which relates with the informatics and computational aspects of the biological systems. So with the ability to process complex biological data at unprecedented speeds, quantum computing promises to unravel the mysteries of genetics, accelerate drug discovery, as I emphasized earlier, and pave the way for groundbreaking medical advancements. Now, bioinformatics is the art of translating the vast sea of biological data from DNA sequences to protein structures into meaningful insights. Traditionally, this involves heavy computational processing that can take years for classical computers to complete. Enter quantum computing, where the rules of quantum mechanics allow for a mind-bending computation speedup. Consider the challenge of protein folding, a fundamental mystery in biology. Proteins, the workhorses of the cell, adopt intricate three-dimensional structures that dictate their functions. Now, determining a protein's native shape is computationally intensive and vital for drug design and disease understanding. Quantum computers have the potential to simulate these processes with incredible accuracy and speed, revolutionizing our understanding of life at the molecular level. Now, genetic sequencing and quantum acceleration. Genetic sequencing, a cornerstone of modern biology, involves decoding the sequence of DNA bases that make up an organism's genome. This information is vital for understanding genetic diseases, identifying potential targets for drug development, and even uncovering the evolution of species. Now, quantum computing's parallel processing capabilities can accelerate this process exponentially. The algorithmic prowess of quantum computers allows for rapid comparison of DNA sequences. So in bioinformatics and molecular biology and computational biology, it is important to compare DNA sequences. So these are done by by using various alignment tools, and quantum computing can enhance these alignment tools, identifying genetic variations that contribute to diseases, and providing a comprehensive view of an organism's genetic makeup. Now, drug discovery and quantum simulations. The field of drug discovery is poised for a quantum leap. Quantum computers can simulate molecular interactions with unparalleled precision, providing a platform for designing drugs that fit specific molecular shapes. This has the potential to revolutionize the pharmaceutical industry, speeding up the development of new medications while reducing the risk of adverse effects. Now, quantum simulations can model how drugs interact with proteins, predicting their efficacy and potential side effects. This could significantly reduce the costly and time-consuming trial and error processes involved in drug development, leading to faster discoveries of treatments for diseases that have long eluded conventional approaches. So it is also notable that conventional approaches lead to undesired side effects, which may be reduced by designing drugs using quantum simulations and quantum computing. Now, biological data compression and quantum AI. As the amount of biological data grows exponentially, efficient data storage and analysis becomes paramount. Quantum computing has the potential to revolutionize data compression and storage, enabling scientists to store vast amounts of genetic and molecular information in a compact and easily accessible format. Additionally, quantum machine learning algorithms can mine massive biological datasets for hidden patterns, facilitating the discovery of new biomarkers, diagnostic tools, and therapeutic targets. Quantum AI holds the promise of uncovering relationships within complex biological systems that classical computers might overlook. So we have even for fundamental understanding of complex biological systems, we may need quantum machine learning to model the biological systems. And of course, that would have practical advantages also. Now we will talk about a field called quantum biology. So quantum biology is the investigation of quantum phenomena in biological systems. Now, quantum biology and quantum computing, two seemingly disparate realms, converge at the cutting edge of scientific exploration. Quantum biology delves into the enigmatic role of quantum phenomena in biological processes, unveiling the subtleties of photosynthesis, enzyme reactions, and more. Now, while quantum computing is still in its infancy, it is progressing at a remarkable pace. As researchers continue to refine hardware, software, and algorithms, we each inch closer to unlocking the full potential of quantum computers. Governments, academia, and industries are investing heavily in quantum research and development, recognizing the transformative effect it could have on various sectors. Now, as we navigate this uncharted territory, collaboration between physicists, computer scientists, mathematicians, and domain experts will be pivotal. The challenges are immense, but so are the rewards. Quantum computing holds the promise of revolutionizing industries, solving problems previously deemed unsolvable, and reshaping the boundaries of what is possible in computation. Now, conclusion. Embracing the quantum leap in agriculture, key takeaways, revolutionary potential. Quantum computing holds the promise to transform agriculture, offering unprecedented precision and efficiency in farming practices, innovative solutions, from optimizing crop yields to enhancing supply chain logistics. The applications of quantum computing are vast and groundbreaking. Sustainable future. By harnessing the power of quantum technology, we can address global food security challenges and promote sustainable agricultural practices. Moving forward, continued research, invest in ongoing research and development to unlock the full potential of quantum computing in agriculture. Collaborative efforts foster partnerships between tech companies, agricultural organizations, and research institutions to derive innovation, education, and training. We equip the next generation of agricultural professionals with the knowledge and skills to leverage quantum technologies. So as I told you, we are working towards installing quantum computers at ICR ISRI, the organization where I work. And final thought, quantum computing is not just a futuristic concept, it is a powerful tool that can help us cultivate a more sustainable and prosperous future for agriculture. This is my contact information, email monendra_grover@yahoo.com, and this is my LinkedIn. And I would like to conclude by saying by Einstein, I want to know how God created this world. I'm not interested in this or that phenomena in the spectrum of this or that element. I want to know his thoughts. The rest are just details.
Very, very inspiring and impressive talk, Dr. Grover. Thank you and congratulations. Congratulations on getting the funding from the National Quantum Mission in India. So really
Thank you.
appreciate that. Um, so I think one of the things that comes to my mind is you in your prior slide, you said you are open for researchers and tech companies to collaborate, right?
Yes.
I- And is that only limited in within India or other places as well?
Yeah, we may explore, but we are waiting the further input from National Quantum Mission, and we will have several meetings. And as we go into the meetings and decide the future course of action with our funding agency, we will keep you posted.
So thank you because we have a lot of researchers who will watch this thing, and I think this might be a good opportunity for them to see what it takes, and even get involved in some ways. So really,
Yes, yes.
really appreciate that. Um, I'd like to open up for questions. I know we have 5 minutes remaining. I want to respect everybody's time. It's especially Dr. Rover. It's around 11 there or 11:30-ish there, right?
10:30.
Yeah, 10:30. Okay, okay.
Yeah.
Yeah. So with that, I'll open up for questions. That is there any questions anybody has for Dr. Grover?
Hello.
James, I see you unmuted yourself, sir.
Hi. So I did have a question about, so it was an earlier question as mentioned on when we would be able to see practical applications that we can use for quantum computing. And you mentioned that the answer to this might be a little bit complicated, but uh, is there an estimate on how long it would take based on your understanding of this?
Yes, I think it may take at the pace at which technology is processing, it may take few years, and in the worst case scenario, a decade. I don't see it taking more than a decade even in worst case scenarios. And hopefully, and if we go in positive side, it may take a few years because the research is progressing very rapidly.
I see. Thank you.
So I have a question. So the quantum
Yeah.
computer that we are gonna type install in India, uh,
Yes.
who is developing that quantum computer? Is it homegrown
Yeah.
in India or is it
Yeah,
from?
it is actually it is a private company, QPI AI, which
Okay.
is Nagendra Nagaraja is the CEO of that company, and they are uh, importing some of their parts from Finland, I think. It
Mm,
is some is manufactured in India, but mostly it is from Finland, and they are assembling it here. And it is a company which is a global sort of company, and so they are utilizing their contacts in other countries also.
got it, got it. No, thank you. Appreciate that. I see Michelle has a question. What types of AI models do you think are the most likely benefit from quantum computing?
Yeah, that is, in fact, LLMs are in vogue now, and I saw many reports which combine the effects of quantum and LLM, and in fact, it would be very good because LLM is has already resulted in so much speed and efficiency, and quantum is known for its speed and efficiency, and combining the powers of both. In fact, the work is already underway, and in fact, it was in my last talk. There was a participant who asked this question, and I went and searched for quantum LLMs, and I was excited to see that the quantum fields and LLM fields, they are now being combined to produce maximum efficiency. So LLMs, I think, would be the most important field that would be benefited by quantum and vice versa.
Got it. Got it. Thank you. Michelle, does that answer your question? Do you have a follow-up question? Okay. Yeah, she said yes, thank you. Any other questions, anyone? Okay. If not, this is great. Thank you, Dr. Grover. With this, we conclude your two-session talk. I really appreciate and thank you for coming here and speaking to the audience. We will be posting this video soon and I'll send you the link.
And there is one more question.
Oh, okay. Okay. Why don't you answer that? I don't see it on
Yeah,
my.
yeah. How postgraduates can you just a minute?
Oh, it's your purse to you directly. Okay.
Okay. How postgraduate students in India work as a research intern in your organization. So we hire them as young professionals. We categorize them as young professionals 2, 1 at various stages. We have research associates, we have senior research fellows. So all of these young postgraduate students can come and work with us. So once we go into the deeper into the move forward into our journey into establishing quantum computers, we would advertise the positions, and young students interested in quantum computing can join us for this journey.
Thank you. Thank you for answering that. I think that's it. Then, with that, thank you. Have a good night, Dr. Grover, and thank you everyone from wherever you're joining. Really appreciate this time. Thank you.
Thank you, Taposh, and thank you, everyone. I
Thank you.
had a nice time.
Yeah, no,
here.
thank you. This was very inspiring talk. Thank you.
Yeah. Thank you.
Okay, bye.
Bye.